It's my pleasure to introduce Dennis Keiser today. Dennis is president of Keiser Corporation. He received his Bachelor of Science degree in Mechanical Engineering from California State Polytechnic University. Since then, he has devoted his life to the advancement of human performance. After several years of designing conventional weight stack machines, Dennis began testing an idea to use compressed air and pneumatic cylinders as a source of resistance over a wide range of exercising speeds. Keiser's first production machine debuted in July of 1978 and was soon being utilized by a large number of NFL teams. Today, over 70% of the NFL, Major League Baseball, NBA, NHL, and the major soccer teams in Europe utilize Keiser in their training programs. In 1984, Keiser built the first computerized strength training machines to measure work, speed, and power produced during each repetition at a given resistance. Today, Keiser's Air 420 10-rep test is used by many teams to determine a player's readiness to return to play after an injury. In January of 1994, Keiser received a Small Business Innovation Research grant from NASA to design and build a single-station, multifunction exercise device to be used by astronauts during long-duration space flights. Dennis has never wavered from his goal and passion to dramatically improve human performance and to do it more safely. As a result, today, Keiser leads the world in speed and power training. Dennis Keiser.
Thank you, Troy.
You bet.
That wasn't what I wrote. I purposely wrote it in a way that separated me from the company. The reason I did is that the message that I want to deliver this morning is so important, too important, to be prejudiced in your minds because I'm also a manufacturer of exercise equipment. I got into this industry 44 years ago. I learned very quickly the limitations that we have in dealing with the current technology. And all I wanted to do was to take human performance to a higher level. One of the things I noticed on the slide a little earlier was the conference 2017 was about improving athletic performance. It's not about how much I can bench press or how much I can squat. It's about athletic performance. I prefer to say human performance because we deal in all spectrums of human activity, not just in sport. Now, the title of this is The Value of Self-Evaluation. As such, and as an engineer, one of my gifts, I guess, is that I have the ability to step back periodically and really look at where I'm going from a design standpoint, from a corporate standpoint, but to be able to step back and very honestly assess where I am and where I'm going. And am I on the right track? Is this going to take me to the future? Is this design going to take me where I want it, or am I going to run into a dead end? And today I want to do the same thing with you. We have to periodically stand back and say, what is my real mission? What do I really want to accomplish? Do I want to make bench pressers out of all of these guys? Do I want to make squatters out of all of these guys? Or is it really about athletic performance? If it is, then I've got to look at athletic performance. Now, I know if we're going to stand back and we're going to look and assess what we've been doing, I'm treading on some very hallowed ground. There'll be some people that will walk out of here saying Dennis did nothing but trash iron and trash Olympic lifting. That's not my purpose. I have a great deal of respect for the fathers of Olympic lifting in the United States. It's brought us a long way. The ability to use mass and gravity has brought us a long way. But at some point, we have to stand back and say, is the future simply an extension of the past? Is the past and my past success going to carry me into the future? Is strength the only thing that is important in human performance? Because we have put such an emphasis on strength. You're called strength coaches, that we've forgotten the others. There's two parts to a movement: the force we produce and the speed at which we produce it. But we've totally ignored that speed component. Now, lately, we're talking about speed-based training, velocity-based training, which is a good thing. Now we've got to assess what is the right way to train our speed. And it's really not just about speed. It's about strength at game speed. And so what I'm going to do is I want to take us through a variety of scenarios so that I can open your mind to where I see the future of human performance. Now, this started last year after the banquet when I talked to Chuck and I challenged Chuck on the future. I said, Chuck, are we really improving human performance? How much human performance can we really take credit for? How many world records can we really take credit for? How much of it's technology? How much of it's running surfaces, shoes, pole vault poles, swim gear? And how much of it is really us? Because we have to be honest with ourselves. Are we accomplishing what we need to accomplish? Or are we just doing things because that's what we're used to doing? I feel that over the last 2 decades, that we really haven't done much more than just churn through the same thing. Einstein says if the definition of insanity is doing the same thing over and over again and expecting different results. Is Einstein right? Have we been insane? Or are we just expecting the same results we've been getting? When maybe we're not expecting better results. Or maybe we're just following our colleagues. A couple of years ago, I was talking to the strength coach for a professional baseball team. I knew he was an Olympic lifter. I knew that that's what he liked. So I asked him, I says, what is it about the Olympic lifts that you really like? He ignored my question, didn't answer it. Thank you, sir. He ignored my questions, didn't answer it. So we talked for another minute or two. I asked him again. I says, what is it about the iron that you really like? Still ignored the question. So another minute later, I just said, why do you do what you do? Frustrated at that point, knowing he was not going to get away from this question, he said, tradition. As an engineer, there's a reason for everything I do. And for our engineers, they have to be able to answer any question I ask about their design, right down to the dimension and the tolerance on that dimension. If they can't give me a reason that they have that particular tolerance on that dimension, then they're in trouble. And certainly any coach at the highest elite level in our industry, in professional sports, ought to have a reason for everything they do. For him to answer tradition is an insult to the industry. But I'm afraid that's a lot of what we do. The MLB in 2015, according to Kitman Labs, spent $700 million on players that were injured and couldn't play. over $23 million paid to players that couldn't play, average, every team. And you guys are begging for money for your weight room. Do you own this? Because as performance coaches, not strength coaches, as performance coaches, as the chief mechanics for these high-performance engines, because that's what you are. You're the chief mechanic for these high-performance engines. And as such, you have to build that engine for that race. And if that engine breaks down halfway through that race, you own it. It's yours. No excuses. Well, he sprained his ankle when he hit the bag, or hurt himself sliding. That's the engine you have to build. I own it. A friend of mine, one of the top coaches in the world, gave me a response to a question that very much disappointed me. When I asked him why a player pulled a hamstring at the beginning of a game in a very important series. Now, he was the coach for that player. I says, what happened? He said, oh, the coach is pushing him too hard. He didn't own that problem. If you don't own it, you can't fix it. I owned that problem because he was using our equipment. I owned it. Why didn't he? Fran Tarkington said, I look back at my life, I've learned nothing from winning. I really learned from failing. Just to fail is not enough. You've got to own your failure. Michael Jordan says, I've missed more than 3,000 shots in my career. I've lost almost 300 games. 26 times I've been trusted to take the game-winning shot and missed. I have failed over and over and over again in my life, and that's why I succeed. 3 things are keeping us from going forward. Einstein and our insanity, continuing to do the same thing and expecting different results. Not owning our failures, and being afraid to fail. We have to get away from this comfort zone. We can no longer be afraid to fail. I know that you all have worked hard to get where you are in your careers, and you do not want to lose your job, especially at the high level. But we have got to keep pushing. We cannot let the fear of failure prevent us from moving forward. If we're going to take human performance to a higher level, we have got to answer these questions honestly. Why do I train slow to play a fast game? We train our athletes slow to go out and play a fast game, and then we wonder why they were hurt. The brain is very neuroplastic. It remembers all of these slow speed movements. We're setting them up for failure in the weight room. Why am I so concerned about our athletes being hurt in the weight room? Why does the coach tell you, I know you got a job to do, just don't hurt my guys? Why do we associate speed with danger? Why do we build a strength base first in rehab? Why are we so fixated on strength when there are 2 parts to a movement, the force we produce and the speed at which we produce it? Why do we recruit fast athletes and focus on making them stronger? Why do we think the Olympic lifts are a powerful movement? Maybe these curves can help explain. This happens to be a leg extension machine, knee extension. Now, it's a variable resistance machine. That's why we drop the resistance a little bit at the beginning. We reach maximum resistance at the middle. And as we reach full extension, we drop the resistance. We have to respect the shearing forces on the knee at 110 degrees of flexion. So we start light, we get heaviest at mid-range, and then as we reach full extension, the quadriceps have shortened to the point where they just don't have the contractive effort, and we have to lighten the resistance. On a very slow repetition, you can see in the red curve in there, that red that you see, that's the weight stack. The blue is what we really want to hold. So you can see on 4 seconds out, 4 seconds back, we fit the curve perfectly. Even at 2 seconds out and 2 seconds back, a 4-second repetition, a little bit of extra force at the beginning of the range of motion to get the weight moving. But not so bad that it's dangerous. This is why our standard training protocol is out on 2, back on 2. Because anything more than this, we go out on 1 second and back on 1 second. That's just this fast, guys and gals. That's just this fast. Terribly slow compared to game speed. But we've already increased the resistance at the beginning of the range of motion by almost 50%, and we've lost 40% at the end. We step it up a little bit more and we go out on a half second and back on a half second. That's this fast. Still incredibly slow by game speed standards. Incredibly slow. But we've already doubled the resistance at the beginning, at a point in the range of motion we're most vulnerable to injury, and we've lost 80% at the end. Now, the first thing we have to understand is, where does the resistance come from the tools we're using? So if we take a mass-based system, mass gravity-based system, we have to use Newton's second law. Force equals mass times acceleration. Also can be expressed as force equals mass times gravity. If I take the mass of an iron plate and the Earth's gravitational acceleration acting on that mass, that's the weight of the plate. That's the number stamped on that plate. But once I put that plate into motion, I have to combine both of those formulas. So what I have is the actual force that I'm going to feel on my hands on that bar is what I think I'm lifting, mass times gravity, plus that same mass times my acceleration. How much acceleration do I put into it? And that's going to depend on how fast I want to move it. The faster I want to move through that range of motion, the greater my acceleration. Hence, the greater forces I'm going to have at the beginning of my lift. This is all due to the second half of the equation, and so is this down here. This is all positive acceleration, and this is negative acceleration because I am decelerating. I'm slowing down. Now, I said the brain was neuroplastic. It remembers these things that we put it through. What am I teaching the brain to do halfway through my range of motion? Teaching my brain to slow down during the last half of the range of motion. Teaching myself to slow down. At a point in the game or in my range of motion where I play the game. I play the game from 0 degrees of flexion back to about 40 degrees. So in that range of motion where I'm playing the game, I have no resistance and I'm teaching the brain to slow down. This is why we can't train speed with iron. The beginning of the range of motion, I don't play the game here, but this is where I end my career in the weight room because of the shock loading. So let's go back and answer those questions. Why do I train slow to play a fast game? Because I can't have this and I can't have this. So I have to train slow. Why are we so fixated or concerned about our athletes being hurt in the weight room? Same thing. This is why we train slow and why we take such chances on injury when we try to do ballistic movements in the weight room with mass. Why do we associate speed with danger? Because we know that speed behind the iron is dangerous. I know a lot of coaches that believe in speed of training. They won't do it because it's dangerous. So it's holding us back. Why do we build a strength base first in rehab? Because we can't subject our patients to this kind of stress. We've got to build that strength base first. We've got to heal that soft tissue first. Then we can start to bring on the resistance. Why are we so fixated on strength when there are two parts to a movement? The force we produce and the speed at which we produce it. Again, we really can't address the speed component. Why do we recruit fast athletes and focus on making them stronger? Again, because we cannot train them for speed. Why are the Olympic lifts considered to be a powerful lift? It's because of this down here. The Olympic lift is the only lift we can do that we don't have to intentionally slow down that weight. That we can explode all the way through that lift and never once intentionally slow that weight down. This is why the Olympic lifts are considered a powerful movement. Because they eliminate this intentional deceleration. We're able to explode all the way through this lift, bring that bar into an area where we are incredibly weak, let gravity slow it down, and so we can pop under it. This is also why we flip tires. This is also why we throw medicine balls. Is to eliminate this part of that curve. Because we can let go of these things. As long as we understand this stuff, then we understand our tool. Then we know how to get the most out of it. I'm not here to trash it. I'm here to make sure that we understand the tools we use. We need to focus on this speed component. We're not training speed because speed is dangerous. There's nothing that says that if I move my arm real fast, it's going to fly off my body. No, we're not training speed because the modality we've been using doesn't work. It has a place, but it doesn't have a place in the velocity-based world. It has a place in a pure strength-based world, but not in a velocity-based world. When we get into a velocity-based world, when we really, really focus on athletic performance, and we start with a blank sheet of paper, a very open mind, and say, what is that engine that I have to build to propel a bobsled? And this is Ben from the British bobsled team, and we've been working with the British bobsled group. And it's an easy example to use, and they've been so good to let us use all of this stuff, so I'm sharing it with you. But it's an easy example because in a bobsled, if you got 4 guys pushing a bobsled, they're the engine propelling that bobsled. There's no question about it. They're the engine. Now the question is, what kind of engine do we build? We've got a driver. He's the first one in the sled. He's going to have to start that thing. We need all the force we can get out of him and all the power we can get out of him at a very slow speed because he's in that sled before there's any real speed. Then the next guy has to be a little faster, a little faster, and a little faster. Ben is the third guy in the sled. That's 240 kilos, so 528 pounds. Over 5,000 watts at 528 pounds. The guys that were competing down in the booth hit 5,000 watts, but they're at 600 and 800 pounds. You try to do it at these real low resistances, you've got to have a lot of speed. This will give you an idea of what he does on a box jump. This is 1 meter high. Watch again. It's like nothing to him. He's like a gazelle. Now, the reason he's not jumping higher, he's only jumping about 40 inches. The reason he's not jumping higher is watch his head. Whoops. Watch his head in the ceiling. He's got his head touching the ceiling. Now, I can't say that he's still the right engine. And while that looks impressive, it doesn't matter to me if he can't push a bobsled. So it's not about box jumping either. It just looks impressive. This is Brad. He's a driver. Now, he's doing it 550 pounds, 250 kilos. His power's at 5,300 watts right now. But even then, that may not be the right engine. And watts, as much as we talk about power, and Keiser talks about power all the time, the future isn't just about power. It's about how we get the power. I can get 400 horsepower out of a diesel truck engine, and I can get 400 horsepower out of an automotive engine. Totally 2 different engines, same horsepower. So power is only part of the equation. It's how we get the power, and that is how much strength and how much speed contributes to that power. The guys that are generating 5,000 watts in the competition at 800 pounds are like diesel truck engines, which is okay if you want to pull 40,000 pounds. He's more like a Formula One engine, which is okay if you're going to be a Formula One car. Both are right. There's nothing wrong with either one. It's a matter of how they fit the job. To figure out what kind of engines we have, and Troy talked about the Air 420. That's our dynamometer. You put a race engine on a dyno to check its power and its torque, its strength, all the way through its RPM range. Well, we do the same thing with the human engine. To understand the human engine, we take it through its entire force velocity curve. So that line running diagonally across there is the force velocity curve. Unlike the force velocity curve that you have in your textbooks. Because your textbook curve is underslung. Got a slope to it, or a sling to it. It's because it was done with iron. When you do it with a pure force, you get a straight curve. Allows us then to extend that straight line to the x-intercept and the y-intercept. X-intercept tells us how strong that individual is at zero velocity. The y-intercept tells us how fast that individual is at zero force. Both somewhat fictitious numbers, but a good fingerprint for what kind of engine we have. Now, to give you an example of an engine that was totally designed wrong, I want to show you the Firefighter Combat Challenge. Now, these guys are wearing turnout gear, breathing apparatus, boots, and gloves that weigh about 45 pounds. They're going to reach down, and they're going to pick up that hose pack, and that also weighs 45 pounds. They're going to skip every other step going up. They're going to run up the equivalent of a 4-story building. They're going to get to the top. They're going to reach over, they're going to drop that hose pack. They're going to reach over. They're going to grab this rope and that hose pack, and they're going to hoist them up. The blue one and the red one. Now, power is force times velocity. But power can also be expressed as doing a certain amount of work in a given amount of time. Now, work is force times distance. The resistance that they've got are both 45 pounds. They're going to hoist both of them exactly the same height. So both are doing exactly the same amount of work. So therefore, the person who raises it the fastest is the more powerful. But this is only 45 pounds. You guys handle 45-pound plates all day long. It's nothing. But you watch how much slower one of these athletes is over the other. And these guys are very, very good athletes. Now, I want you to pay particular attention to the first two evolutions, because going up those stairs, they're carrying 90 pounds over their body weight. The guy on the right's a little bit more powerful. Now, look at him on the right. Look how fast he's hoisting that up. Look how slow the other guys. Look at that thing fly over the top. The guy on the left is like a diesel truck. The guy on the right's like a Formula One. So now you've got to build the right engine for this race. We pick up a 172-pound dummy and drag him 100 feet to the finish line. That guy on that left lane is going to lose this competition by just about what he came out of that tower at. He lost everything in that tower, pretty much. We tested 160 plus firefighters on the Air 420. I happened to test this guy. I said, man, you're strong. You're the strongest firefighter we have ever tested. He was very proud. He puffed out his chest. He said, yeah, I like to do squats. I said, well, it shows. I said, let's see how powerful you are. When I saw his power was just a little bit above average. Power is force times velocity. Where was his speed? I said, man, you're slow. As proud as he was of how strong he was, he looked me straight in the eyes, and he said, it shows up on the stair climb. He knew he was slow. He knew it. He kept trying to get stronger to get faster, and all he did was make himself slower. Why in the world does he need to be able to leg press 1,400 pounds when he is carrying 90 pounds over his body weight up those stairs? It's not about strength. It's about strength at speed. We have got to understand the game that we're playing, the race that we're running, and design the engine accordingly. He needed to drop that strength side and focus on building the speed side. And having the right amount of speed for that race and the right amount of strength to propel his body and that hose pack and that turnout gear up those stairs. That's all he needed. This is one of the first charts that comes out of the Air 420. This happens to be a professional soccer player. All this is doing here is comparing the power in one leg versus the other. That's all it's doing. We're just looking at the power that the left leg is generating and the right leg is generating. Now, the resistance is the same on both legs, so the only difference is the speed component. He tore an ACL, had surgery, went through rehab. This was his test while he was going through rehab. I don't know how close this test was to when they returned him to play, but when they returned him to play, he was re-injured. They determined that the soft tissue was okay. They did not use our test. They had our machine, they did not use it, or did not understand it. That was our fault. They used their Biodex or Cybex or whatever they had for testing that they were used to, determined that he was ready to return to play. Soft tissue's the same. I mean, the strength in both legs was the same. And it is almost all the time. Once they get rehabbed, it's right there. The problem is the central nervous system never got rehabbed. Velocity is brain driven. I would like you just to do this. Just do this for me, please. Just a simple exercise. Everybody, just do this. See, you can listen to me, and I can continue to give this speech and continue to do this, and we basically just do this brain dead. But the very second that I ask you to go from here to here, as fast as you possibly can, just do that one time. Focus, just go as fast as you possibly can. You tuned me out. You tuned everybody out. 100% of your thought went into that movement, and you weren't even moving a resistance. All you were doing was thinking about moving from point A to point B as fast as you possibly could go. It is very, very much brain-driven. When we train velocity, we are training the brain. It's not muscle. We're training the brain to control that muscle, to make that muscle do what it wants it to do at the exact moment it wants it done. This is an NFL football player. Tore a patella tendon. 2 surgeries. First one failed. 2 surgeries. A lot of trauma to the knee. After the surgery, went into rehab. We sent some equipment down to help. Rehab was obviously very good here. We did not test him when they returned him to play. He got back into play, got a Super Bowl ring the year the Giants won. But then they released him. So I told the player, I said, why don't you come up to Fresno, let's test you, because we never tested you. When we tested him, this is what we saw. And I tell you, the therapist did a fabulous job. He's within 5% all the way through. Until he gets to the high resistances. Keep in mind, that Air 420 gets heavier and heavier and heavier on each rep until he can't do any more. So once he got up to these higher resistances, he didn't have the power. He couldn't generate the speed. So I told him, I said, the only thing I can see here is that you have a problem, may have a problem taking off, because he's a punt returner. He has to move lightning fast once he catches that ball. He said, I already know that. He knew. He knew he was slow, and he had to compensate for it. Well, if he compensates for it, it's going to show up on the films. His coaches are going to see it, and the opposing team's going to know how to play him. They released him. He went to another team. He didn't get it fixed. They released him. Finally, I told him, I said, look, we've got to fix this. At 800 pounds, you have a deficit. 800 and above. 800 sounds like a lot, but to a player, that's 400 pounds per leg. He's 225 pounds himself. He's pushing off with one leg. He's generating way more than 400 pounds. At speed. At speed. These are 3 professional soccer players. Oh, by the way, we did get him rehabbed. We've added about 4 years to his career. The injury would not have ended his career other than the fact he couldn't play the game. He just signed a 3-year contract with the team. So now he's got 4 years of income that he would not have had he not addressed this issue. These are 3 professional soccer players in Europe. Coach was concerned because he says, Dennis, you're telling me that this guy here in red is the strongest guy. But his 1RM, this is where he quit. The solid parts of these lines, the heavy parts of these lines, is where the test was. So this was his last effort right here. He says, you're telling me this guy in red is the strongest guy, and yet he has the lowest 1RM. I says, first of all, you're never going to get a true 1RM out of any professional athlete. That's why we never use 1RMs. I says, there's nothing wrong with the test. You've got 3 players all playing on the same team, all different engines. You've got one guy that's very strong, not very fast. You've got another guy that's in the middle. Then you've got a guy that's about 17% weaker than this guy, but 35% faster than the red guy. Who has to be the most intrinsically quick person on a soccer team? I'm not talking about running speed. I'm talking about quick. A clock that's wound up good and tight. Who? 100%. That's the goalie. So now we can start to pick out these engines. We start to understand the engines we're dealing with. The future is not about strength. But it's not about speed either. It's not even about power. It's about all of them. None more important than the other. The only time strength becomes more important than speed is when I've got an athlete that needs more strength in the position that he's playing. The only time speed becomes more important is when I've got an athlete that's strong enough to play that position, but he's too slow. Power to weight ratio starts becoming important. I hold you guys to the highest level. You need to expect more out of yourself. You need to be that chief mechanic of these high-performance engines. And when you own the problems, if somebody gets hurt, if I got a football player that's got his spike stuck in the turf and he gets hit from the side, do I own that problem? Damn rights. I own it. You know why I own it? Because if I could have made him a couple of milliseconds faster, could he have gotten those spikes out of the turf just before he got that impact? Maybe. Could have maybe saved him an ACL. That's the future of human performance, athletic performance. I think we're about up on time, and I've got to respect the next speaker. Got 4 minutes. I'll take a question if somebody has one, or even a challenge. Yes, sir. Each repetition Each repetition becomes an individual repetition. Like we're used to popping reps out and looking at the volume. But each repetition becomes its own repetition, meaning that if I'm going to, and it doesn't matter, the weight, the resistance is going to determine how fast I can really move it, because my intent is going to be to move it as fast as I possibly can. So if I'm working at 80% of 1 RM, like I would typically do for a heavy lift, that's going to make me rather slow, but I'm going to sit here and I'm going to focus and I'm going to fire as fast as I possibly can, or I'll start out here and I'll come back and then I'll pop it out as fast as I can go. I'll hold it, I'll gather my thoughts, because just like I did with this, it takes that mental concentration to connect that brain to that muscle. I'll fire it back. I'll gather my thoughts, I'll come back, and I'll fire out the next one. Now, when I have done, because the brain is very neuroplastic and it's going to remember what I've done, I do not want it to remember a really slow speed. So when I have done 2 repetitions under 90% of my best, max power that I generated, and your max power will stay there on the display, and what you'll see on the left of that will be the percentage of that rep, of that max power for each rep. So, and the reason we do that is so that you can coach to that. So when you have done 2 consecutive repetitions below 90%, you're done. That's done. If you do 1, it just means that you probably got a lapse of concentration. And you'll fire another one back, you'll get it back together, and you'll fire the next one back, and you'll be above 90. But eventually, you're going to fatigue, and you will have 2 consecutive reps below 90. That's how you look at the training for power, training for the speed component. So it's not just about pounding out reps. We've really got to connect the brain to the muscle. And when we do that, we get a lot of other benefits, because now we've got much better coordination of that muscle, much better control. We coached Mike Powell for when he broke Bob Beeman's long jump record, and Mike still has that record today. But because he was so fast and so strong, he could do well over 500 pounds, 7 repetitions in 5 seconds. And he had legs that looked like a distance runner's legs. But when his foot hits that board, a lot of things have to happen really, really fast. And so being able to get the brain to make that muscle do exactly what it wanted it to do, to put an isometric contraction, to hold and store that energy so that when he launched in that concentric contraction, he was able to take advantage of the elasticity. That all happens because the brain is now in such good control of the muscle. So not only are we developing the speed component, but we're developing that whole coordination and control of that muscle. I want to thank all of you very much for today. I had a coach spend a day with me a while back. Took him to the airport, and he's a professional NFL coach. Took him to the airport. We got there early enough to sit down and have a beer. And while we were drinking this beer, I kind of lost him. He was just in thought. So I just kind of watched him for a bit, and pretty soon he noticed me looking at him, and so he looked up and he says, "Dennis," he says, "I'm 59 years old. I'm nearing retirement, and now you're making me think. I hope I've done the same thing for you." Thank you.